pleasure to introduce Colleen Robles from Duke University, who is going to tell us about period matrices and applications. Colleen?
Yeah. Thank you, Ludmil. Thanks you to the organizers for the opportunity to speak. And thank you to all the speakers. I've really been enjoying the talks. They've been great. So I'm going to spend a lot of today talking about a structure that's come up in several of the other talks, and those are representations of period maps by period matrices. And I'm going to focus primarily on a case that we haven't seen yet, which is the case that the period domain is not Hermitian, which is a little more subtle because those domains don't have realizations in affine spaces, which is roughly equivalent to saying that there's no globally defined period matrix representation for the period map. But I'd like to explain when we do have these structures and how this can be used to study the geometry of period maps at infinity, and in particular to get completions of period mappings. And this is motivated by a desire to look at, to use the Hodge theory that's associated with these completions to study boundaries of compactifications of moduli spaces. So one of the moduli spaces that's received a lot of attention recently from this perspective are the eye surfaces that we've already seen in a couple talks. Okay, so let me just start with matrix representations, and this is very much familiar, and it's going back to a classical perspective. And I really do mean what it sounds like, which is that we can represent the period map by a period matrix. So as we've already discussed, the Siegel upper half space, or the Siegel half space H sub G, this is the collection of all G by G symmetric matrices with complex entries and with imaginary part positive definite. And what's important here is the well-known fact that this is naturally identified with the period domain D that parametrizes weight equal to 1 polarized Hodge structures on some rational vector space of dimension 2G. And just to emphasize the perspective that I'm going to take later, what I mean in particular is that you can choose a basis. This has to be a complex basis, but you can choose a basis of the vector space so that this map that takes one of these pre-approved matrices in Siegel space and tells you what the first subspace in the Hodge filtration is. So it sends it to F1, which will be V10, and it's spanned by VI plus AI VA, where here I runs from A to G and A runs over the rest of the indices. Okay. So you may recognize that these are just Plucker coordinates. on the Lagrangian Grassmannian, which is the compact dual in this case. So period matrix representations, in fact, are just Plucker coordinates. And I'll say more about that. But this case is not special within the Hermitian symmetric realm. It's a, what did I do? It's a general fact that every Hermitian symmetric D may be similarly parametrized. By matrices. Okay. And this is a fairly classical fact that goes all the way back to Cartan, at least. And the way to think about that is that if I can parameterize my Hermitian symmetric domain by matrices, then using the coordinates of those matrices, that means I can think of D as sitting inside some complex affine space. So I have lots of functions on D. I just take the coordinate functions. And this embedding here is not unique, and that's been important in applications. So for example, you get both the bounded and unbounded realizations of the Hermitian symmetric domain that both played a key role in the construction of the Satake-Bailey-Burrell compactification of the arithmetic quotient, and have were also used in the toroidal compactifications or desingularizations. Yeah. But the upshot for all of this, at least in the Hermitian symmetric case, is that the period map then and I'm always going to assume that B is smooth, that the period map admits a multi-valued. Period matrix. Okay, and of course the multi-valuedness is coming from monodromy, which is being indicated by the discrete subgroup that I'm quotienting out by gamma. So this story assumes that you're mapping to a space that is locally Hermitian symmetric. Okay, it fails in general. So so in general, the non-Hermitian D admit no such realization. Okay, and the reason for that is because D contains, in general, compact subvarieties. C, and that means that you can't put D inside an affine space. Okay. So in particular, in general, there exists no global period matrix representation. Of phi. Okay. But we do have them locally, as I'll discuss in a moment, both inside the domain and out at infinity, thanks to Schmidt's nilpotent orbit theorem. And most of what I want to talk about today is how we get a global at infinity period matrix representation and what that's good for. So I'll have to describe what I mean by global at infinity. And I'll do that when I get there. Okay. So today is about when does a period map admit a period matrix representation, and what's it good for? And there are two answers that I'll talk about. The first is it gives constructions of completions of period mappings. Okay. That's the object that we want to study compactifications of moduli spaces. And it gives us one handle to study what I'll call the global geometry of period mappings at infinity. Okay. So the local geometry for period mappings at infinity is given to us by Schmidt's nilpotent orbit theorem. But what I want is the following. So Schmidt's theorem is a statement that's over a local coordinate chart at infinity. So in particular, the period mapping will probably not a priori be proper when I restrict to that punctured coordinate chart. I need neighborhoods of compact varieties at infinity, where I have a period matrix representation and the period map is still proper. So when I say global at infinity, one sort of very informal way to think about this is that I'm asking to extend some consequences of Schmidt's results from local coordinate charts into very nice neighborhoods of compact varieties in the boundary. And I'll be more precise about that when I get to describing those varieties. So let me start with a question of perspective that I already alluded to when I mentioned Plucker coordinates, and that is where do period matrices come from? Okay. And the answer is basically that they come from Zariski open coordinate neighborhoods on the compact dual, which are Schubert cells. So in particular, the compact dual, which remember is the set of filtrations that satisfy the first Hodge-Riemann bilinear relation, but not necessarily the second. So they're isotropic with respect to the polarization. This is covered by Zariski open Schubert cells. On S, which are affine spaces. Okay, and so what's going on here is that S is actually a coordinate chart, and this identification is just the coordinate map. Okay. But this map is giving us the matrix representation. And in the Hermitian case, the domain is contained in a single coordinate chart in the compact dual, but that's false in general, as I discussed a moment ago. But,
Colleen, can I
yeah.
ask?
Hey, Patrick.
Oh, hi. But Griffiths has a conjecture, right? That if you go to the universal cover, the map, you can factor the thing through, I think, a Stein manifold, or maybe it's I forgot the conjecture, but I think, I think, yeah. I mean, are you going to say anything about that conjecture? Is what you're saying related to that conjecture?
I guess so I'm not sure I'm about to answer the right question. Repeat your question.
Well, I asked it vaguely, but that he has a conjecture that the period map, if you go up to the universal cover, it factors through, I believe, a Stein submanifold of D hat, or maybe.
I don't immediately see how closely related this is. So I think that's interesting. Maybe we can say something out at infinity. But I think it's related. I don't know how closely.
Thanks.
Okay, so let me just give you one more example. So, and I'll come back to this one so we can talk about a non-Hermitian example later, but to give you a feel for how this works. So maybe we could take the period domain, which parameterizes weight equal to 2 polarized Hodge structures on some rational vector space V, and let's say for convenience that the Hodge numbers are 2B2. Okay. And I'd like to say that the dimension of this vector space is D+1. Then in particular, the compact dual is just the Grassmannian of Q isotropic 2 planes inside the complexification. And given some F2, which will be my V20 inside the compact dual, I'm going to describe the coordinate chart around it, the Zariski open Schubert cell that contains it. So the way you do that is you fix a basis, which I'm going to index a little oddly, V0 to V1, V2, yada, 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 all the way down to V2 bar, V1 bar, and V0, where here, of course, A bar is D minus A. And then F2 what C will be the span of VI plus CIA VA, where here we let I run from 0 to 1 and A is greater than or equal to 2. So what I've written so far here describes a map from, let's see, I guess this is going from 2 times, oops, into the full Grassmannian of 2 planes. And then the Hodge-Riemann bilinear relations, the first one, this determines 3 of these coordinates. It determines 0, 0, 1, 1, and it determines 0, 1 plus 1, 0. So if you take that into account, then what you end up with is S, which is the set of all of these 2 planes, which will determine the full weight 2 Hodge structure with C in C2D minus 5. And this is Zariski open in D. Okay. And then we'll say that these elements of S admit a matrix representation, which is just, it's just the coordinate map. So 1, 0, 0, 1, and then C 2, 0. So all I'm doing here is describing this basis of F2. But the upshot the upshot of all of this is the following. So phi, we have some map, some period map admits a matrix representation. If first gamma preserves S, and that's not quite correct. Of course, you really only need it to preserve the intersection of S with the domain, but preserving S is certainly good enough. And the image of the period map itself takes values in the discrete quotient of the intersection of that Schubert cell with the domain. So let's suppose now, I haven't been really precise about this notation, that B is smooth and quasi-projective with a smooth projective completion and normal crossing divisor at infinity. Okay. And this will be the running assumption now. Okay, so the first remark is that the fact that phi is locally liftable, let's assume that gamma is acting without fixed points inside the domain. This implies that phi locally admits a period matrix representation. Okay, I mean, this is obvious. This is sort of the trivial example. I'm just saying that if you pick a point inside the period domain D, you can find a little coordinate neighborhood around it. The period map lifts to the compact dual, the period domain, and in particular the compact dual. You just take a Schubert cell containing it, and you're done. You can also, thanks to Schmid, do this out at infinity. Okay. So the nilpotent orbit theorem tells us that every point B inside the boundary at infinity admits a coordinate neighborhood. Let's call these coordinate neighborhoods U bar contained in B bar, so that phi admits a period matrix representation. over the punctured coordinate neighborhood U. And let me talk about a specific example. So you might consider the case, let's just do something one-dimensional, that's fine. Your coordinate neighborhood might be the unit disk. So the punctured coordinate neighborhood will be the punctured disk. Less than 1. Okay. And let's look at the Hodge structure that would underlie the variation that arises when you take a curve of genus 2 and you let it degenerate by acquiring a node. So something like this. Okay. Then in that case, the local period map out at infinity, which will be tracking for us the first subspace in the Hodge filtration. This is spanned by 2 vectors, and their basis is represented by a matrix of the following form. Alpha T. Okay. And so these 3 are holomorphic, and they extend to be holomorphic on the whole disk past the puncture. This is not holomorphic. This is where the nilpotent orbit lives. This is where we have a log term. So in particular, alpha T, lambda T, and nu T minus 1 over 2 pi I times log T. These are holomorphic. And in fact, they're holomorphic on the unpunctured coordinate neighborhood. But in particular, notice that this implies that alpha lambda and the exponential of 2 pi I nu, these give us functions from this coordinate neighborhood into C3. Of course, in general, here the monodromy is very simple. It's just the monodromy coming from log. And once we move to larger sets, the monodromy will be much more complicated, and we will not have this straightforward way of getting functions. But the goal is the following. So we want, as I mentioned, neighborhoods inside the compact dual of certain compact varieties. A sitting inside the boundary at infinity, so that first of all, phi admits a matrix representation over that punctured neighborhood. And second, when I take phi and restrict it to that punctured neighborhood, it's proper. And we're also going to get a little more out of this, but I'm not ready to say yet. Say what yet? We need some definitions. Okay, so the goal is to construct these neighborhoods and then use them to study the geometry at infinity and to study completions of period mappings. So let me next turn to period maps at infinity, and these are going to be induced variations of limiting mixed Hodge structures, or quotients of them. So I need to break the boundary down into smooth strata, smooth pieces. So let's let Zi be the irreducible components of our boundary R, and then take the intersection over all I in a specified range. And then the open strata that I want to look at is the complement of this closed strata with the substrata removed. So this is going to be Zi minus the union over I contained in, but not equal to J, Zj. So, you know, I'm sure you've seen this picture, but let me draw it anyways. So this is maybe Z1 star. Here's, oops, Z2 star, and finally here we have Z1 2, which is just Z1 intersects Z2. So on each of these open strata, we're going to get a variation of limiting mixed Hodge structure. So in particular, given a point B, in one of these strata, the nilpotent orbit theorem associates to this point a limiting mixed Hodge structure. And so this is the data of a weight filtration, a Hodge filtration, and a nilpotent cone. Now, as long as I restrict to a tubular neighborhood of this strata, then the weight filtration and the cone, well, I said that not right. The weight filtration and the cone are independent of our choice of point B inside that strata. They might depend upon the overall monodromy, but if I restrict to a tubular neighborhood of this strata, the only monodromy fixes the cone, and therefore the weight filtration centralizes the cone and fixes the weight filtration. So these are well defined and independent of B. The Hodge filtration, on the other hand, both depends on B and is not well defined. Okay. So what is well defined is the nilpotent orbit. And here I mean just the set of all Hodge filtrations swept out by taking the exponential of the nilpotent cone. So this is some subset of the compact dual. So this is well defined. But the upshot of all of this is that I get on this open strata a variation of limiting mixed Hodge structures. This Zi star phi I that maps into, well, I have to mod out by the action of the cone. And I have to mod out by the action of the monodromy along the strata. So here, I need to save a little space. So gamma I, this is the monodromy. About Zi, and it centralizes centralizes the nilpotent cone of logarithms of monodromy. And so in particular, it fixes the weight filtration. Okay. So for convenience in a lot of the talk, I'm just going to assume that the monodromy is neat. Okay, so let's write this map as saying that phi I maps the point B to the equivalence class of the weight filtration, the Hodge filtration, which depends on B, and the nilpotent cone. Then I want to pass to a quotient. So this, because this is a limiting mixed Hodge structure, that means this Hodge filtration induces a Hodge filtration of a pure polarized Hodge structure on the weight graded quotients, and it's polarized by the nilpotent cone. So I can pass to a quotient which will wipe out the ambiguity in the nilpotent cone and get an oddness to goodness variation of polarized Hodge structures. So this is a variation of polarized Hodge structures along the strata. And this is where I'm going to start to look for my compact varieties in the boundary. Okay, so this second map, this phi I naught of B, this is mapping to the Hodge filtration on the weight graded quotients, and it has a family of polarizations coming from the nilpotent cone. So here GRWL is WL mod WL minus 1. Now, one way to think about what's happening here is that this map is modding out all the extension data. So the fiber is the collection of all limiting mixed Hodge structures that have the same weight graded quotient. And what's left to vary then in that fiber is extension data. In the Hermitian case, I get a little ahead of myself. I'll stop there. Okay. So these maps patch together. So the phi I not patch together. To give a proper continuous map. That I'll just call phi naught, defined all on B bar. And let's call the image of this space P bar naught. So I'm not going to discuss the strata. It's like the stratification on B bar for the following statement. It's slightly coarser than the one we have been discussing, but there is a stratification on B bar so that when this map is restricted to the stratification, the map is not just continuous, but it's analytic. So it's analytic and proper. Okay, this is basically a stratification that's determined by the weight filtration. And if I denote the image of the period map by B, then this is open and dense in this P bar hat, which right now is just compact and Hausdorff and stratified by analytic varieties, but compact and Hausdorff. Okay. So two things go into the proof. So the real problem is to get Hausdorff, and then everything else more or less follows. So you need two things for Hausdorff. If you're working locally, patching these maps together locally in one of Schmidt's coordinate charts at infinity, then basically what you need is the several variable SL2 orbit theorem, or its implication, the relative weight filtration property. Once you want to do this globally, then you need a finiteness statement. And that finiteness statement you can get from a result that basically asserts that the image of the period map is contained in only finitely many Siegel sets. In the case of a one variable degeneration, this is in Schmidt's paper. And for several variable degenerations, it was proved a couple of years ago by Bakker, Bernarbe, and Zimmerman as part of their work to show that the image of the period map is quasi-projective, which Patrick was telling us about. Okay, so in special cases, the situation is a little bit better than this suggests. So first, if D is Hermitian, then this map phi naught up here, this is Borel's extension. Of the period map. Well, if D is Hermitian, and I guess gamma is arithmetic, to B bar and the Sataki-Bailey-Borel compactification. Okay. And then in that case, this P bar naught is the image of that extension. So we conjectured with Redu-Laza that something similar is true. So in particular, the conjecture is that the augmented Hodge line bundle which Kang introduced in his talks, and I'll come back to this in a little bit, that this is semi-ample. Okay, so that means some sufficiently high power of it is base point free, so that in particular, we get a geometric object. That geometric object is the image of this map. Augmented Hodge line bundle, and this a priori just continuous map from B bar into B hat is a morphism of algebraic varieties. Okay. So maybe just a couple of remarks. So the first is that, as already alluded to in this comment up here, the conjecture holds in the Hermitian case. So the conjecture holds if D is Hermitian and gamma is arithmetic. That's the classical case covered by Sataki-Bailey-Borel. And it also holds when the dimension of B is less than or equal to 2. So for dimension equal to 1, this is a consequence of the work of Somesi and some results on the churn form of the augmented Hodge line bundle that's in the paper with Green, Griffiths, and Laza. And the case when the dimension is equal to 2, this is an argument based on the Hodge index theorem, which is also in that paper. And perhaps one more remark. So this beautiful result of Bakker, Brunarby, and Zimmerman, they prove that the image of the period map is quasi-projective. And one implication of their argument is that the augmented Hodge line bundle is semi-ample over B. Okay, and so this is close to what we want, right? But we need semi-ample over all of B bar, over the compactification. So the first set of fibers, or the first set of compact varieties that we want to study period maps in a neighborhood of are fibers of this phi naught. So I stated a slightly weak version of this theorem, but I mentioned that there are strata on which this map restricts to be proper and analytic, which means by the proper mapping theorem that the fibers are analytic varieties. And the conjecture leads to this question of what can we say? About the phi naught fibers. Okay. And what can we say about the period map in a neighborhood of them? So we're basically claiming they can be collapsed in a very nice way. So let me tell you what is the first sort of structural result that we can say about them. And so this is a period matrix representation about those phi naught fibers. Okay, so again, those fibers are compact and they're parametrizing extension data for a family of limiting mixed Hodge structures that have all of them the same associated weight graded Hodge structure. So the theorem is the following. So let's let A naught be a connected component. Okay, it's necessarily compact. So it's a compact connected component of a phi naught fiber. So this is the period map of pure polarized Hodge structures along the strata. And for convenience, I'm going to assume that this is irreducible. Okay. This is just so that I can make some statements in the talk a little more cleanly, but is not necessary. Then the theorem asserts that there's a neighborhood, O bar naught, contained in B bar, of A naught and a Schubert cell S, so that first the monodromy. Gamma naught over phi naught, which is the punctured neighborhood, preserves S. And the image of the period map on that punctured neighborhood takes value in a quotient of that Schubert cell. So in particular, these two statements here are saying that phi has a matrix representation over this punctured neighborhood. And then the third statement is that, in fact, we have the desired properness. So in fact, the full extension is proper. So in particular, phi restricted to O naught is proper. Okay, I don't think I said it explicitly, but I am making the simplifying assumption that phi, the global phi, is proper on B. So let me say a couple of words about what goes into the proof. So remember the local picture that we get from the nilpotent orbit theorem. So if I'm working locally, I have a nilpotent orbit, and maybe this is F, and let's just do one variable for convenience. I have a nilpotent orbit that approximates the period map out at infinity in one of these local coordinate charts out at infinity. And you can use this to define this F infinity, which is the limit as the imaginary part of Z goes to plus infinity of expzn dot F. This is independent of various choices. And this defines what you might call a sort of reduced limit period map. So it defines a map on the strata, again, that takes value in the topological boundary of the period domain inside the compact dual. And in fact, it takes value in a real group orbit, although we don't need that. But what is important is that that phi I naught factors through this map. Okay. That's a straightforward statement. That's just something that falls out of the definition of the quotient and the structure of the limit at the boundary. Okay. So we have a picture that looks something like this. Let's call the image of these two maps P, and P infinity and P naught I. Okay. So this was our original variation of polarized Hodge structure, and this is sort of our variation of, well, maybe just call it, I'm going to make up names for this. It factors through this map, and then the remarkable statement is here the infinitesimal period relation tells us that the fibers are finite. Which is remarkable. It's remarkable outside the Hermitian case. Inside the Hermitian case, it's a trivial statement because if D is Hermitian, then that implies that that map is just an identification. P infinity I is P not I. These images here are basically the boundary components in the Sataki-Bailey-Burrell compactification. But the upshot of this that's important is that that means that we can choose this neighborhood O naught bar so that the monodromy in the punctured neighborhood preserves F infinity. And that in turn, of course, implies that gamma naught preserves the complex conjugate of F infinity. And so in particular, gamma naught preserves the Zariski open Schubert cell of filtrations in the compact dual that intersect this F infinity conjugate generically, so with a minimal possible dimension for this compact dual. And I'll just write that as dimension EP. Is minimal. And this is a generic condition. And the Schubert variety contains the Hodge filtrations for all of the limiting mixed Hodge structures for points inside this fiber that we're considering. And that's enough to conclude the theorem. Okay. So I think I'm about out of time, so I'll stop here, but I'll start with some consequences of this result and refinements next time. This is sort of the first structural result we need to get going.
Thank you very much. Any questions? All right, if there are no any questions, let's thank Colleen again. And we'll proceed tomorrow at 9 a.m.